Okay, this is the last meeting of the year, which is really sad, but it's also been really fun, and today's going to be really cool. Okay, so news of today is that I think exactly a week ago, China landed a rover on Mars. And so I kind of forgot to do the news of the day for this. So we're just going to watch a video. Um, I saw a good one over here. Yeah, this one's short. So yeah, there's a bunch of like news articles on this if you want to check it out. It's definitely worth checking out because like there's some like key differences between the Chinese rover and the Perseverance rover. So like here, just pop that in there if you want to read more about it. Okay. Moving on to today, we're talking about gravitational waves. And specifically, Eric and I wrote a paper, like a little paper about gravitational waves and the conservation of energy. So that's what we're going to be doing today. First, Eric is going to talk more about gravitational waves in general, give a little intro.
Yeah. So yeah, we worked on this paper in ARP 2. Some of you might have been ARP 1. But yeah, uh this actually I won't get into the paper yet. We'll just start with the basics, which is what happens when stars die, which so as you know, a star forms when you have a nebula, a dark nebula specifically, and then when something sparks fusion, it'll begin fusing in bulk globules, and then it'll create a protostar and all that good stuff. So eventually it begins fusion. And in its life, it has this continuous process, um, a continuous balance between fusion and gravity that's pushing in on itself. So this is a very delicate balance. If gravity is too strong, then the star will crush in on itself and implode. If gravity is weaker than fusion, then the star will explode outwards. So yeah, in life, the star always has this delicate balance of fusion and gravity. And in death, this depends on the mass of the star. You have three types of star deaths. The first is the white dwarf, when you have the stellar remnant, which is basically the core of the star. So generally, all stars or most stars will become white dwarfs. Our sun will eventually become a white dwarf. Typically, it's when it stops fusion at around carbon and oxygen, and it's extremely dense. It's only about the size of the Earth, but it has basically entire mass of a star in it. So you can just imagine how dense it is. Next, we have neutron stars, which, yeah, there you go. Neutron stars. They are ridiculous. They are basically the most extreme things in the universe aside from black holes. These are formed when stars around 8 to 10. Yeah, I think it was 8 to 10 times the mass of the sun, and their life. So basically, oh, and in white dwarfs, in all cases, you get when gravity wins and fusion stops. So you get neutron stars when you have larger stars. So, like I said, most extreme things in the universe, they are formed in supernova, uh, where so a supernova is just a massive explosion. What happens when a star implodes in on itself very rapidly, and then it explodes outwards. Like if you're in ARP1 and you remember Mrs. Stoltz's soda can demonstration, that was depicting how the star will implode in on itself, and the pressure causes it afterwards to explode outwards. So yeah, they are formed in supernova. They are really small, only like 20 kilometers long, which means that they're around the size of cities. The entire mass of a star, a really big star for that matter, packed into a city. So basically, it's ridiculously dense. It's so dense that we actually don't know what happens inside of it. Like, a lot of the information around the cores, what's inside neutron stars, is unknown to us because we don't know what happens in such extreme conditions. So yeah, these things are ridiculous. But so these are one of the types that produce gravitational waves. The next is the black hole. So black holes are the most extreme things in the universe. So yeah, they are created when a star upwards of 10 times the mass of the sun die. So oh, 20 times the mass of the sun. I was wrong. Yeah, so they are so dense that not even light can escape. So, which is why they are called black, because we can't see them with the naked eye. So yeah, they have an event horizon, and they're the event horizon is commonly known as the point of no return, because that's when um, not even light is able to escape. Um, so they, like I said, they appear black to the human eye. So they're insane. And neutron stars and black holes, the reason why we need to talk about this before getting onto gravitational waves is because they're the things in the universe that produce gravitational waves. Well, a lot of things produce gravitational waves, but these two especially are what produces what's detectable to us. So yeah. Oh, I have a nice picture of a black hole. Yeah, this was taken, was it 2017? This was the first actual picture of a black hole that we ever got, which is amazing. Uh, what's after this? What I put? Aha, yes, collisions. Okay, that's the bit that we're talking about today. So the collisions of neutron stars and black holes, or neutron stars and neutron stars, or black holes and black holes, these cause gravitational waves because, or detectable gravitational waves is what I should say. Although they are huge collisions, massive collisions, and they send giant ripples throughout space-time, these ripples throughout space-time are known as gravitational waves. The reason why I said detectable is because many things do produce gravitational waves, but at the same time, only a few things can give off such intense amounts of energy that we're able to detect them using the technology we have here on Earth. So yeah, how to detect, oh right, this was my slide, right, how to detect it. It's LIGO. So um I actually didn't mention this on the slide, but basically on Earth we've built interferometers specifically designed to detect gravitational waves, LIGO and Virgo. um I might go into how they work. I think maybe we've gone into how they work. If you were there for the ARP1 presentation about gravitational waves, you should know that. So yeah, they were first detected September of 2015, which is wild how recent that is. So yeah, that was a bit of background information on it. Yeah, this is the paper which Jenna, you can put into the chat for
I don't know
people.
what I just did. Okay. So do you think we have enough time to like read it? Or should we just get to the explanation?
I think we can just do the presentation. That's fine.
Okay.
So
But just like real quick, this is our paper. Yeah, got purpose. What can produce gravitational waves, how to visualize them, and then the conservation of energy part, which was like our main question. And then yeah, okay.
Oh, am I doing this? Oh, yeah, I am. Okay. So flashback to ARP1. That's what. So what I meant by this is that if you were in ARP1, then you remember I did give a presentation on gravitational waves. And if you were really paying attention and you stayed till the end, then you might have remembered that one of our members asked a question, which was how gravitational waves don't violate the conservation of energy. So the reason why this is like really important is because if gravitational waves do violate the conservation of energy, we have a big problem. And that's that the laws of physics might need a little bit of changing. If they don't, then thank goodness we can sleep well at night. To answer this, what gives off gravitational waves? In the original presentation, I believe we said that everything gives off gravitational waves, but that's not true, as we found from our research. So, Jenna, why don't you go ahead with that?
Oh yeah, okay. So the things that produce gravitational waves are called time-varying quadrupoles. Um, but so let's define what that means step by step. So first we're going to define what a quadrupole is, and then we're going to define what time varying means. So what is a quadrupole? So we have this quadrupole moment, which is the second moment of mass. But what do we mean by moment? The definition of moment is an expression involving the product of a distance and physical quantity. And in this way, it accounts for how the physical quantity is located or arranged. So for example, if we have torque, tau equals F, the force, times R. And so this is the first moment of force, where the physical quantity is force, and we have R is the distance to the first power. So it's the first moment of force. So if we had like some expression that was like FR squared, then that would be the second moment of force because it's to the second power. So the quadrupole is the second moment of mass. And so we can kind of see that moment definition manifesting in this definition of the quadrupole moment tensor here. So this is the quadrupole moment tensor, Ij. It's a function of frequency, and you can see that we've got like position vectors yi and yj, and then we have this t00. And so T00 is the zeroth component, the top left component of the stress energy tensor, which you might remember from our general relativity stuff, is going to be the energy of the system. And so by Einstein's mass energy equivalence, if we have this energy T00, then that accounts for the mass part of this. And then we have yi and yj, which are position vectors. And so if you're multiplying two together, then that's kind of like distance squared. So you can see how the definition of a moment is manifesting in this equation. So we have that Iij is the quadrupole moment tensor of the energy density of the source of the gravitational wave. And so what that means is that if we have like two black holes are colliding and they're giving off gravitational waves, then that point where they're colliding is going to be the source of the gravitational waves because that's where they start and spread out from. And so the quadrupole moment tensor is going to describe the energy distribution at the source and outwards. So we said that this Iij is the quadrupole moment tensor of the energy density of the source. And so how does quadrupoles even play into gravitational waves? So we said that T00 is the time-like component of the stress energy tensor, which is energy. And again, by mass energy equivalence, when we have energy, we have mass. And so when the quadrupole moment changes, when it varies, that means that we're changing the energy, we're changing the mass. And so that motion is causing the ripples in space-time, which are the gravitational waves. So that is the explanation of what quadrupole means. And then we have time varying, which literally just means that it changes with time. So if we have a time varying quadrupole, then that just means that we have a quadrupole that's changing over time, which, as we said, is what's generating the gravitational waves. And so if you want more reading about quadrupoles and stuff, you can check out this set of lectures on general relativity on page 149 there. Okay.
Okay, yeah. So now that we've defined what produces gravitational waves, we can go about getting a grasp on how we can determine whether or not they give off energy or not. So we get this really cool physicist, Richard Feynman. He published a thought experiment anonymously at the time, basically saying this. So gravitational waves, we all know, stretch and compress space-time. Now say you have a bead on a string. When the bead moves, then there will naturally be friction between the bead and the string. So this friction is basically thermal energy. So what he's basically saying is that because gravitational waves impart some sort of energy into the bead and the string, this produces thermal energy, which means that they do carry energy. So this is basically an argument for that gravitational waves carry energy. And this is very hypothetical. Later, Feynman did claim that, yes, I did do this. So I guess when it became successful, he's like, yeah, I did this. But anyway, yeah, so this is just a thought experiment. This is just basically speculation about it. At the same time, it does hold merit because LIGO, the Laser Interferometer Gravitational Waves Observatory, basically bases all its work upon this. Because if gravitational waves have a physical effect, then they're able to be detected. LIGO does detect the physical effect that gravitational waves have. So this kind of proves Feynman's thought experiment. But this is just one argument, and we're going to go over a lot more.
Yeah, so now that we have this idea that gravitational waves do carry energy, now the question becomes, do gravitational waves obey conservation of energy? And so to look at that from a theoretical perspective, we're going to talk about Noether's theorem. And what Noether's theorem says is that conservation laws like conservation of energy and conservation of momentum come from symmetries. And so what a symmetry is a physical or mathematical feature of the system that is preserved or remains unchanged under some transformation. And so to kind of like explain what the heck that means, let's look at the example of a circle. So if we have a circle and we have a rotational transformation, meaning that we're just going to like rotate it a little bit. If you rotate a circle, it's going to literally be the exact same after you rotate it. So circles have rotational symmetry. If you have like a square and you rotate it by 90 degrees, then it has rotational symmetry in that way. It has discrete rotational symmetry because it only is symmetrical under discrete values, but I'm getting ahead of myself. I hope so. Yeah, that is what a symmetry is. But anyways, so Noether's theorem says that different symmetries lead to different conservation laws. And so the key to theoretically determining do gravitational waves violate the conservation of energy, we need to look at the symmetry that leads to energy conservation and see if gravitational wave systems have that symmetry. So, oh wait, I got ahead of myself again. So how do we even tell if a system has a certain symmetry? So if you transform the quantity corresponding to the symmetry and the system remains unchanged or invariant, then it has that symmetry. So like if we use that circle example that we have before, so we're transforming the circle, we're transforming it with a rotation and the circle is unchanged. So it has rotational symmetry. So yeah. Okay, moving on to applying this to gravitational waves. So we are looking for, do gravitational waves have energy conservation? The symmetry that is related to this is temporal symmetry, time symmetry. So let's just think about it if it has this symmetry. So if you take a gravitational wave system, like the entire thing, and you just like pick it up and let it exist at any other time in the universe, would the physics of the system change? would the gravitational wave system behave any different if you just like plunked it at some other point on the timeline of the universe? No, it wouldn't. It would still be the exact same. So therefore, gravitational wave systems have temporal symmetry and therefore energy conservation. So that is the theoretical aspect of energy conservation.
Okay, yeah. So that's a theoretical perspective. To put it into a bit more concrete terms, we do have an experiment to look to, or an observation to look to. So we get these two scientists, Hulse and Taylor. In 1974, they detected two orbiting pulsars. So these pulsars are, yeah, they were detected by the combination of LIGO as well as the telescope by Hulse and Taylor. So Taylor and Weisenberg, one other scientist and one of the original scientists, decided to use an equation to try and predict the decay of the orbital period of the binary pulsar system if gravitational waves do carry energy away. So to put this into perspective, so you have two pulsars orbiting each other. As time goes on, they will give off gravitational waves. As to if these gravitational waves actually give off energy, if the gravitational waves do give off energy, then their orbital period should decrease by a certain amount. So Taylor and Weisenberg decided to calculate what would happen if they give off energy, how much the period would decrease by. And yeah, exactly. They use equations from if gravitational waves did have a real physical effect. So they used a window of 8 years. They came back to this experiment in 1982 and collected some data on if gravitational waves had caused that decay, that expected decay over that certain amount of time. And they found that yes, it did. It matched very, very closely within its experimental uncertainty. And this basically confirmed experimentally that gravitational waves do give off energy, and that they do not the reason why this is important is because they don't violate conservation of energy, because they have a real physical effect that actually negates this. So does that make sense? I don't know if I feel like that might have been a bit confusing.
It's okay. If they see the document in the chat, they can read it again.
Yeah.
Yeah. Oh wait, sorry.
So we might need to send that. So for the person who just came in, here's the document. You should be able to take a look at it. So yeah, if you guys are a little unsure about this, you can revisit the document and take a look. So yeah, that's the experimental aspect of it. And now we get to the conclusion. So in conclusion, have we found new mind-boggling physics that makes it so gravitational waves actually violate the conservation of energy? No. Gravitational waves do not violate the conservation of energy. We found this through the thought experiment, Noether's theorem, as well as the experiment by Taylor and Weisenberg. So unfortunately, we won't have some super exciting thing where gravitational waves actually violate the conservation of energy. We won't have to rewrite any physics laws. No. So yeah, sleep well at night. And that concludes our presentation.
Yeah. So yeah, that was gravitational waves and conservation of energy. Like we said, you can like read our paper more if you want to read it more. I don't know. And so that's the last meeting of the year, which is really sad. But this club has been really fun this year, and I definitely learned a lot. So yes, I think as far as like the club next year goes, I'll probably like hit up the group chat in the summer about like officers and stuff, so we can figure all that stuff out then. But yeah, that's just about it for now. Have a good summer, everyone. Thanks for coming as always. Yeah.
Awesome stuff. Thank you.